Last video I made this soft robotic gripper, and today I'm gonna design a 4° of freedom robotic arm for it. Well, that's a lie, I've already done that. But I'm gonna go back in time. I'm gonna pick the specific components and design a PCB which will link them together. Then I'm gonna order it, so I should be building the arm by the next video. Okay, let's do it. This video is sponsored by PCBWay. I drew the schematic about a week ago, so I'm gonna take a picture in case I forget it. This is my shitty drawing of the robotic arm. It has 4 degrees of freedom because it has 4 motors. And if you can't tell, this is the gripper. I'm gonna make the gripper interchangeable, so you will be able to choose a gripper with 3 fingers or a single finger gripper like this one. Or any gripper you want, these are just the 2 I have right now. Let's ignore this motor for now. So the base rotates, these 2 motors rotate, and this is 3 degrees of freedom. This can move the end effector to any spatial position you want. So the spatial position is defined, but the rotation, you can't control that. So that's what this 4th motor is for. So I'm gonna tell the arm to move, let's say here, but I'm also gonna tell it the angle it should be at. So if I want to pick up, let's say a flask, I'm gonna tell it to move 90 degrees. And if I want to pick something up from the ground, I'm gonna change the angle to 0 degrees and pick it up. Okay, now that we have the rough idea, let's pick the main components. Let's start with the motors. I got these spare servos from my hexapod. They are 40 kg and they might not have enough power, but I'm gonna work around that, which you'll see later. These also rotate 270 degrees. Be careful with the 360 degree servos. You usually control their speed, not angle. This could fuck you up. For the pump, I actually have a ton of them because I tried to make at first my hexapod to climb walls with suction cups, and then I tried to make a wall climbing suit. So I have a bunch of these 12-volt pumps. These are all the pumps I have. I got 2 of each. I have these 2 little ones. Then I got 2 large ones. And then I have 2 middle-sized ones which I'm gonna use. I originally got them for my wall climbing suit, which I never finished. That's for the gripper. To control the arm, I have 2 options. I can either use an Arduino, which would be great because I have many of them and I don't plan on using them that much. Or I could choose ESP32, which would be also great because it has ESP now and I could control the arm remotely. I haven't decided which microcontroller I'm gonna use yet, but let's go with the Arduino for now. I also haven't decided which Arduino I would use, because this Nano might not have enough pins. So these are the main parts. I still have to choose a bunch of parts for the PCB and how I'm gonna wire them together. There's one more thing I wanna add. These motors have a high torque, but if you look at the size of this gripper, this arm is gonna have to be huge. This arm is gonna have to be huge. These 2 motors might not have enough torque, and that's why I'm gonna add a constant force spring. This spring should offset the torque of this motor, and it should make it work less hard. I wanted to try a few new things with this robotic arm, and this is the first one. At first, I'm gonna design the pneumatic circuit, because it's the more restrictive one. It's usually harder to find these pneumatic components, so that's what I'm gonna design first, and then I'm gonna design the electronics around it. The main part is this pump, which is gonna be connected to the gripper with pneumatic tubing. I need to know when the gripper closes to stop the pumps. Otherwise, when the gripper is closed and I pump more air in, it's just gonna explode. So I'm gonna measure the pressure inside of the system, and when it reaches some threshold I set, it's gonna cut off the pumps. When the gripper is holding something and I want to release it, I somehow need to get rid of all the air. So I'm gonna use a solenoid valve that will just vent it to the atmosphere. This is an old solenoid valve I bought for the wall climbing suit. If you apply voltage to it, it will energize a coil of wire, and it will move a core inside of it and open the valve. Due to the pressure sensor being big as fuck, I'm gonna have to print some capsule to connect these components together. To connect the components to the tube, I'm gonna use pneumatic fittings, which I'm gonna label as stars. Now I have to pick the pressure sensor, the solenoid, the tube and the pneumatic fittings. I'm gonna do that right now to make sure everything works. For the pneumatics, I'm gonna need some tubing, so I picked this one because it's cheap. It's 10 meters long, which is enough for my needs. And I picked 6x4mm outdoor and inner diameter, so it's compatible with the other components. And the 4mm inner diameter should be enough to deliver the air quickly to my gripper. I don't have that fast of a pump. To connect the tubing to something, I'm gonna need pneumatic fittings. These fittings are great because you can press on the blue stuff and you can connect or disconnect the tube quickly. These ones also come with this M5 thread, and since the thread is metric, I'm gonna be able to screw them into these heatset inserts. They usually don't make heatset inserts for these other American threads. For the pressure sensor, I thought I was gonna find a bunch of these for cheap, but the only one I found that isn't expensive is this BMP 180, and I can't use it because from the description it's only used for weather and stuff like that, and I think I'm gonna need higher pressures. So the other one I found is this industrial pressure transducer. This is expensive, it's quite big, but it can read high pressures, which is what I need. So I'm using this one. From the description, it just works like a variable resistor, and it's powered by 5 volts, so I will be able to read it with Arduino easily. They come with different pressures. I wasn't sure which pressure I was gonna need, so I asked ChatGPT and it told me the expected pressure for pneumatic grippers is about 0.5 to 1 atmospheres. I also googled what is the pressure inside these party balloons, and it looks to be about 0.1 atmospheres, which is nothing. My guess is that the pressure inside my gripper is a few times higher than these party balloons, so I opted for 1 to 2 atmospheres, which is about 40 psi, so I picked the smallest pressure transducer they have. I could have picked the largest just to be safe, but then I would lose the resolution, which is what I need. This pressure transducer also has this weird 1/8" thread. They don't make heatset inserts for this thread, so I bought this adapter, and I'm gonna use this adapter as a heatset insert. Lastly, I picked the solenoid valve. I picked this one because it comes with these pneumatic fittings, which the tubing fits into. And it's also 12 volts, which is great. 3S LiPos are about 12 volts, which I need for my pump. I also need 7 volts for the servo motors, so I have these 2 voltages available, and this solenoid is 12 volts, so I can power it with the battery. Right, we got the pump, we got the gripper, now we pick the pressure sensor and solenoid, so we got everything. For the connections, I've picked a tubing with 6mm outer diameter. The pump doesn't accept the tubing, so I'm gonna use a larger tubing to connect it to the pump, and inside the large tubing I'm gonna put the pneumatic tubing. This isn't pretty, but it should work. This larger tubing has a 5mm inner diameter, so the 6mm pneumatic tubing should fit into that. It's kind of weird, but it's all I got. To connect the tubing to the 3D printed capsule, I'm gonna use the pneumatic fittings, and I'm gonna put M5 heatset inserts into the 3D print. So this is sorted, the gripper same thing, 2 pneumatic fittings and M5 heatset inserts. For the solenoid, this is great because it has already the pneumatic tubings inside, so I don't need to even attach it. And for the pressure sensor, I was able to find only a single pressure sensor, which is from USA, so it uses Freedom units. I think it has 1/8" thread or something. And from what I can tell, there are no heatset inserts for this. But I found an adapter, which I'm gonna use as a heatset insert itself. So I'm gonna heat the fuck out of it, and I'm gonna press it hard as fuck into the hole. And if this doesn't provide a decent seal, I'm just gonna fill it with glue. Thank you, America. Alright, we got all the connections and all the components for the pneumatic circuit sorted, so we can move on to the electronics. Let's start with the power. The pump and the solenoid both need 12 volts, and the servo motors run on 5 to 7 volts, but I want to get the max power out of them, so I'm gonna use 7 volts. These are the 2 main voltages I need. So for the 12 volts, I'm gonna use a 3S LiPo battery. Not this one's pretty shit. And I'm gonna step it down with a buck converter to 7 volts. Alright, so I got the battery. it's gonna run through a switch so I can power it on and off. It's gonna go through DC to DC buck converter, which reduces the 12 volts to 7 volts. And now I got the two main voltages I can work with. At first I'm gonna power the Arduino with 7 volts. Then I'm gonna power the servo motors. And these servo motors are gonna communicate with the Arduino by 4 digital pins. Now for the pressure sensor, it's gonna take in 5 volts from the Arduino and it's gonna output an analog signal which will tell the Arduino what pressure it's reading. Now for the pump and solenoid, these need to be powered by 12 volts, which the Arduino can provide, so I can't use the Arduino's digital pin. I have two options. I can either use a relay or I can use a transistor, and I'm gonna use the latter because it's more elegant. Let's draw the first transistor. I'm gonna call it TS for solenoid, and it's gonna take in the digital pin from the Arduino and 12 volt signal from the LiPo battery. And it's gonna output 0 or 12 volts depending on the value of the digital signal. So if the digital signal is on, it's gonna power the pump, it's gonna power the solenoid by 12 volts, and if it's off, it's just gonna be off. I'm gonna do the same thing for the pump. Oh, and I know this schematic is trash, but I don't have much time, and I'm gonna draw it properly in KiCad later. Alright, I got the pneumatics, I got the electronics, and now I somehow need to control the arm. The arm has 4 degrees of freedom, so I'm gonna use one joystick to control the X and Y movement. And I'm gonna have a second joystick that will control the height of the arm. That's 3 degrees of freedom. And for the rotation of the gripper, I'm gonna use the second axis of the second joystick. These joysticks also have buttons. If you hold one button, it's gonna close the gripper. And if you press it twice, it's gonna open it. Or I'm gonna hook it up to the second joystick. I don't know yet, it doesn't matter. Each joystick has 2 analog signals and 1 digital signal. That's 4 analog signals and 2 digital signals in total. I'm also gonna add this potentiometer, which will control the pressure threshold of the gripper. So if I set it high, the gripper is gonna close hard. If I set it low, it's gonna close only slightly. So in total, that's 6 analog signals and 8 digital signals. The Arduino Nano has enough pins to support the analog and digital signals, so that's what I'm gonna use. The components have been chosen. The schematic has been drawn. Now I somehow need to take this schematic and plug it into my PC to then make a PCB, which I'll be able to plug the components into. And then I'm gonna order it with my sponsor, PCBWay. PCBWay provides PCB assembly, CNC machining, and 3D printing. They can even print stuff out of metal, so I'm definitely gonna try it out in the future. They also do other manufacturing stuff like sheet metal fabrication and injection molding, but I mainly use them for the PCBs. I usually try to design the PCBs to be under 100 by 100 millimeters, because then they only cost $5 for 10 pieces, which is really cheap. They currently have a New Year sale, so you can get the stuff even cheaper. But before I order my PCBs, I'm gonna design them in KiCad. I wanna make 2 PCBs. One PCB is gonna be for the robotic arm itself, that's this one, and the second PCB is gonna be for the controller. So the controller is gonna have 2 joysticks, potentiometer, maybe some buttons, and it's gonna send signals to the main PCB of the robotic arm. It would be such that I could have the controller on the robotic arm and control it, or I could move it away and control it through a wire. That's why I need 2 PCBs. The first one is gonna be for the robotic arm, and the second one is just gonna read the signals from the controls. This is the electrical schematic for the main PCB of the robotic arm. I'm not gonna make the whole thing again, I'm gonna make the servo and the pump so you get a feel for it. Also, this is my second PCB I ever made, so if there are any electrical engineers watching this, definitely let me know some tips. I'm just gonna move this away. Okay, I'm gonna start with the Arduino. I'm using Arduino Nano. I'm gonna use the V3, that's the latest version I guess. It doesn't matter what this looks like, it's just a schematic. First I'm gonna add power. I'm gonna ground these 2 pins, and I'm gonna put 7 volts for the input voltage. Gonna rewrite it. I would get the ground and 7 volts connections from the power input, but I'm not modeling it here, so I'm not gonna put it in. Okay, now I'm gonna add the servo motors. For them, I'm gonna use these generic pin headers. The servo motor has 3 pins, GVS, which means ground, voltage and signal pins. I can connect the first pin to ground, and the second pin to voltage, which is 7 volts. I'm gonna move these away. The third pin is the signal, which controls the angle of the motor, and I'm gonna control it with the digital pin from the Arduino. So I'm using D10 here, and instead of making connections like this, it would all get ugly. I'm gonna use labels. I usually name the label by the pin it goes to, so this is D10, and then I just type the name of the connection, so this is servo 0. I'm gonna put it to the D10 pin as well, and now these two guys are connected. I'm gonna add one more thing. So these servos can draw a lot of power. I've read they can draw about 2 or 2.5 amps. So I'm gonna put a capacitor here, which will filter the voltage so it won't drop that quickly. The question now is what size of a capacitor I want to put here. I have no idea, but ChatGPT told me it can be about 1000 microfarads. And there's no datasheet for the servos I have because they are from AliExpress. Okay, the servo is done, it's powered and it's controlled by the digital pin from the Arduino. So now I'm gonna do the pump. I'm gonna connect the pump to these screw terminals, and it's gonna be powered by 12 volts from the LiPo battery, and then it goes to ground. If I let it like this, it would be on all the time. I don't want that. I want to control the pump with a digital pin. The digital pin doesn't have 12 volts or high enough current, so I'm gonna use N-channel MOSFET to control it. It's gonna connect or disconnect the ground. So if the ground is disconnected, the pump won't be powered, and if it's connected, the pump will start pumping air. The MOSFET will be controlled with a digital pin. I'm gonna use D2 for example. You can't connect it like this because it would just blow up. You need to limit the current from the digital pin. So I'm gonna add a resistor here. And again, I got the size of the resistor from ChatGPT because I'm too lazy to read the datasheet. One other thing, this is an N-channel MOSFET, and these work on electric fields. So I'm gonna put one more resistor here. This resistor will go to ground and to the gate. And I'm gonna put high resistance on it. The purpose of the first resistor, R6, is to limit the current which goes to gate. The purpose of R7 is to get rid of any residual electric field. Even if you turn the MOSFET off, there's still gonna be some electric field, and this could mean that the MOSFET would be on. So the purpose of this high resistor is to dissipate the electric field. At least that's what ChatGPT told me. Okay, and this should be fine. So the pump will be connected to 12 volts, and it will be connected to ground based on this digital signal. If this signal is on, this MOSFET will turn on, and it's gonna connect the pump to the ground. And if it's off, the MOSFET will be off. Last thing I do for this is to put a border around it. I'm gonna write pump for this block, and I'm gonna put it here. I also changed the line type. Nice. This is just to make it more organized and look better. The pump also has this Schottky diode. The pump is basically a DC motor. DC motors have inductance, and when you turn off the pump, it creates voltage spikes, and this diode's purpose is to dissipate the energy. So when the pump turns off, the energy doesn't just shoot back through the whole system, and it gets discharged through this diode. I would do this for all the components. I'm not gonna do it in this video because it would take too long and I'm lazy. I'm just gonna go through each component super quickly, just so you can see what I'm gonna have on this PCB. The first thing is power input. Here you inputted a 3S LiPo battery, ground and voltage. It goes through a switch. When you turn the switch on, it powers the buck converter, which steps down to 12 volts to 7 volts. The 7 volts then powers the servo motors, which are down here. It also delivers power to the 12 volts power line, which makes this LED shine. This will be the indicator for the power. Next, I have this pressure sensor. The pressure sensor works like a variable resistor. You input the ground and 5 volt pins from the Arduino, and based on the pressure, it outputs an analog signal. This is read by the Arduino A7 pin. Already went through the pump. The solenoid looks the same as the pump, and it's controlled by the D9 pin. I also added some redundant power pins. One of the most important things is the controller output. This is the output from the second PCB, which I'm gonna show you in a second. And these are all the controls. These are the joysticks, the potentiometer, and the buttons. This is again all read by the Arduino. I also added these redundant general purpose input-output pins. These are the analog and digital pins I haven't used. I've just put them to this pin header. So in case I need them, I can use them. And that's it. Now I'm gonna show you the second schematic for the second PCB, and then we will move on. This is even simpler than the robotic arm schematic. This is optional. It's just in case I used ESP and I wanted to make this wireless. I'm probably not gonna do that, so I'm just gonna ignore it for now. This is the output of this controller, but it's also input for the power. There's gonna be 2 cables, which take in power from the robotic arm and transfer it to this PCB. PCB. Again, I have an indicator light, which will tell me if it's on or off. Then I have 2 joysticks. These will control the 4 degrees of freedom. The joystick also have 2 buttons, and I've put potentiometer and 2 additional buttons. So I have some redundancy and I can use more controls if I want to. I actually had to make the schematic for these joysticks, so I'm just gonna show you how I did it quickly. These are the only joysticks I found the documentation for. It's usually the hardest thing is to find any documentation. This is the documentation for the footprints, and this is the schematic of how the electrical connections are made. We have pins 1, 2 and 3. 1 is VCC, 3 is ground, 2 is output. For the x-axis it's the same, it's just with a dash. There's also this schematic for the buttons. Doing this in the symbol editor is quite easy. You just make any shape you like, and then you just add the pins. Pin 1 is VCC, and it's a power input. I'm gonna put it here. Pin 2 is the output, and it outputs an analog signal. I'm just gonna put passive here. Pin 2 is the output. And then pin 3 is ground. Like this, you can make any symbols you like. Now I'm gonna assign the footprints. These are the physical dimensions of the parts. Again, I'm not gonna do it for all of these components, but I'm gonna do it for these pin headers and for the joystick. Some of the footprints, like these pin headers, you're gonna find in the KiCad library, but something more special, like these joysticks, you're not gonna find them. You're gonna have to create these footprints yourself. Let's start with the pin headers. These are just the generic pin headers for the Arduino. If you measure them, they are 2.54 millimeters apart. We can filter by the library and the pin count and stuff like that. There's 2 versions, it's either horizontal or vertical. If you right click, you can view the footprint. These are the vertical ones, but I want to use the horizontal ones. These are actually bent, so it will not go straight up from the PCB. It will go flush with the PCB. Just double click. Okay, and for the joysticks, as I said, we have to create those, so I'm gonna do that quickly. You do it in the footprint editor. I've already made the footprint, but I'm gonna show you how I did it. This border, that's the maximum size of the component. I'm using this documentation from AliExpress. So this is 9.6 plus 11.6 millimeters. And I added, I think, 2 millimeters to add some wiggle room. Now we're gonna add the holes and the padding. Pad number is the most important thing. You have to name it the same way you did with the symbol. For example, for this button, there's S1, S2, S3, S4. So I'm gonna name it the same way. This right lower one is S1. And this is how you tell the program to connect this pad to the pin. You also need to know the dimensions. This S1 pin is about 0.8 millimeters. For the hole, I'm gonna add some clearance. I'm gonna put 1.1 millimeters. For the padding, I usually add about 1 millimeter or 2 millimeters. Usually bigger padding is better because it's easier to solder. But it can be too big because then it would interfere with the other pins. Now I need to locate it. That's the S1 pin, and I will do the same for all of the other pins. Then I just save the footprint to my library, and I can assign the footprint in the schematic editor. We have everything set up to make the actual PCB, so let's open up PCB editor. I'm gonna start with the edge cuts layer. Here you define how big the whole PCB is. I usually make it 100 by 100 millimeters, so it costs only $5. Then you just click this button to load all of the components, and now you need to position them. Again, I'm not gonna do the whole thing, I'm just gonna wire up the LED. So these are the pin headers I talked about before. They are gonna be on the side of the PCB, so the cable will stick out from the top of the PCB. I usually start by tracing the voltages and signals, and then I save the whole back layer for ground. So I'm in the front layer, FCU, that means front control layer. Take this trace and just connect the correct traces. Since we defined all the connections in the schematic editor, this forces us to not fuck up, so I can't connect these 5 volts to anything else than this. Okay, and the ground layer, I'm gonna put it on the back side. And this LED is now connected. So if we click this button, it's gonna show the viewer. And you can see there is a trace from the 5 volt pin to the diode. After I was done making all the traces, I added some text, so I will know which components go where. I also added this drawing of the soft arm controller. The final step is to fill the layer with copper. After I was done making the PCB, I just saved the Gerbil and drill files and I sent it to PCBWay. Okay, now I'm gonna order the PCBs. So the dimensions are 100 by 100 millimeters. It's a 2-layer PCB and I want 5 of them. I'm gonna choose the black color because it looks cool. The PCBs are gonna cost $5. I don't need them right now, so I'm gonna go for longer shipping, and it's $12 in total. Now I'm just gonna upload the Gerbil and drill files. They're gonna make the PCB and then ship it. These are all the things I bought from AliExpress. I also added some springs, and I'm gonna try to make the arm out of carbon fiber tubes, so that should be interesting. Until the parts arrive, I'm gonna upgrade the gripper and I'll see you then.